In this video, we're going to cover section 2.3, analyzing graphs of functions. So we introduced functions and we talked about the definition, but we're kind of recap it here. A function is a special relationship where each input has only one output. That relationship can be a table or an equation or even a description. But in order for it to be a function, it has to meet that requirement that each input has only one output. And so when we're talking about equations, what that means is each element of x, every x value, our domain, is assigned to exactly one element of y, our range, okay? So what that means is you can't have an x value that goes or gives you answers of two different y values. Every x has to go to just one y. And if we have a graph of an equation, we can do what's called the vertical line test to see if that graph is a function or not, okay? So again, remember I said every x has to go to just one y. So on this example number 1, I'm going to pick an x value. I'm going to pick x equals 1, and I'm going to draw a vertical line right there. So that's the x value, x equals 1. And because, pretend that's a straight line, because that touches our graph only in one place, that means for x equals 1, there is only one y value. And if you continue and you draw a vertical line here at 3 or at 2.5 or anywhere on this graph, anywhere we draw a vertical line, notice it only touches the graph at one point. And that means that our graph has passed the vertical line test. And yes, this graph is a function because every x value only has one y value. But look at example number 2, and you maybe see it right away. If I pick an x value, let's just pick x equals 1 again, just for fun, and I draw a vertical line at x equals 1, notice I touch the graph here and here. So that means the x value, x equals 1, is going to two different y values. That is not allowed for a function, okay? So if you can draw a vertical line anywhere on your graph and it touches more than once, then the answer is no, it is not a function. So that's the vertical line test. It's how we can determine if a graph represents a function or not. Domain, when we're talking about functions, domain is the set or the list of all the possible x values for which the function is defined. Okay, domain, all x values where our function is defined. I think we've seen that definition before, but we do have a couple new things we're going to look at here too with functions. A function can be increasing, decreasing, or constant. And for each of those, we have sort of a mathematical definition. And then I kind of wrote underneath kind of the intuitive definition. Okay, increasing means it's going uphill from left to right. Okay, so uphill increasing means it will be going like this, uphill. Decreasing means it is going downhill from left to right, so this way. And constant means the function is flat, horizontal. Okay, so those are 3 different qualities that a function can take on, and we're going to use those for our next example. So for number 3, over here to the right, we are given a graph. If we did the vertical line test, you would see that that little graph does pass the vertical line test, so it is the graph of a function, and we're going to use it to answer the questions over on the left. So we need to remember about function notation. We did this back in section 2.2. Whenever we have the letter F and then parentheses and then either an X or a number, that is indicating a function. Okay, so we're looking at a function here. And remember that the number that is inside those parentheses, that is your X value. So when we have this notation, f of -4, what it's really asking me is if x is equal to -4, what is the y value? Okay, so it's asking for the y value when x is equal to -4. So we go over here and look at our graph. X equals -4 is right here. And to find where our function is at that point, look up and down. It's right here. Okay, so when x is -4, y is -3. So f of -4 is equal to -3. Okay, then the next one. Now our x value is 0. What is y when our x value is 0? So here's 0. We look up and down. Okay, when x is 0, where are we? We're right here. We're at y equals 3. So f of 0 is equal to 3. What about when x is positive 3? Here's positive 3. Look up and down. Where is our function? It is right here. So when x is 3, y is positive 2. Okay, so that's how we evaluate functions. Now, actually, those were for x values. Now we're going to turn it around. This next question asks, find all the x values. Okay, so we aren't given the x value this time. We're going to find the x values such that f of x is equal to 1. Okay, so this time they have given us the y value. Y is equal to 1, which is right here. So we look left and we look right, and we find our function is in two places. It's here and it's here. So we want to list all the x values where our function has a y value of 1. So that happens at x equals -2. And again, at x equals 4. Okay, then our next question is, what is the domain of this function? Okay, remember the definition is domain is the set of x values. Okay, so when we have a graph, kind of my general thought process is find your smallest x value on your graph. Actually, let's reframe that. Start with the point that is furthest to the left, leftmost point, and circle it. The graph right up here, the point furthest to the left is right here. What is that point's x value? It is -4. And then find the rightmost point. Go ahead and circle it. It's right here. What is the x value of that point? It is x equals 5. Guess what? That is our domain. X values on this graph go from -4 to +5. When we're doing the domain in our interval notation, we always want to do the smaller value first, okay? But you can see if we were to highlight x equals -4 to x equals 5, our entire graph is between those two values. All the x values are in between there. That is our domain. And we can do a similar technique for finding the range, except instead of looking at the leftmost point and the rightmost point, we want to start with the lowest point. Circle it. Well, it's right here. It's the same one, but this time we don't want to look at its x value. We want to look at its y value because we're looking at range this time, and range is the set of y values. So our range for this graph begins at y equals -3. And then, guess what? Find the highest point on the graph. Circle it. Well, there are many points here at this highest point, but that whole section has the same y value. Look at the y value for the highest point or highest part of your graph, and it is +3. So this graph has a range, y values that go from -3 to +3. And if we were to, again, highlight in between there, the whole graph is between those two values. There's nothing lower than that, nothing higher than that. That is our whole set of y values. Okay, then next up, we're going to look at those little new definitions. Our questions here on the right ask us to give the x values. Okay, so we're going to give x values as our answers, where the function is increasing, decreasing, and constant. And I didn't say it here explicitly, but we want to give those x values in interval notation. Okay, we want to know, where's our graph increasing, where's it decreasing, where's it constant? Before we write out those intervals, let's just kind of take a look at the graph. Our graph is kind of in three pieces, right? We've got this section right here. And notice, like, picture you're in a little car. How's this for funny? Okay, you're in a little car and you're always driving left to right. Are we going uphill? Are we going downhill? Or is it flat? Okay, here my car is going uphill. So this is going to be an increasing section of our graph. Oops. And then when we get up here to this point, it changes, right? We're not going uphill anymore. This is a flat part, right? So this is going to be our constant part of our graph. And then when we turn the corner there, what happens? Well, we start going downhill if we're still driving our car, right? And this is our decreasing portion of our graph. Now we just need to take what we've identified and put it into interval notation. Again, remember I said we are using X values for interval notation. So for this increasing part right here, the uphill part, where does it begin and end? And look at the X values for those spots. So it begins right here at X equals -4. It ends, or it stops going uphill right here at X equals -1. We're going to use parentheses because at the end points, it's not really increasing or decreasing, so we don't include those endpoints. But it is going uphill in between X equals -4 and X equals -1. My next line asks for where is it decreasing, and that was this section we labeled over here on the right. It starts decreasing right here at X equals 2, and it stops right here at X equals 5. So it is decreasing for X values in between 2 and 5. It's this little part right here, right? And then it's constant in between. Again, look at the X values where that constant area begins and ends. It begins here and ends here. So it is constant from -1 to +2. Okay, we're gonna try another one of those because they're so fun. This time our graph's not straight lines. It's a nice little curvy graph. It has an endpoint on the left, so it stops right here. But then notice it has an arrow over here on the right, so it does keep going and going and going. Okay, so it's got one endpoint but keeps going. If we did do a vertical line test, we would see that this is a function. Any vertical line would only touch our graph in one place. So we're starting, excuse me, we're starting off again with our function notation. Remember, the number in the parentheses is your X value. When X is 0, what is Y? That's what this f of 0 means, our function notation. So our curve is right here at X equals 0. Notice it also has a Y value of 0. So when X is 0, Y is also 0. Next up, when X is 2, well, here's X equals 2, right? Where is our graph at that point? It's right here. And that point on our graph has a Y value of -4. Whenever we have function notation like this is exactly equivalent to the ordered pair 2, -4. X value, Y value, X value, Y value. Those mean the exact same thing. Okay, domain of this graph. Remember, domain X values, left to right. Okay, so the leftmost point on my graph is this one. Rightmost point, it's an arrow. So what does that mean? Okay, so we're going to grab the X values. The X value of the leftmost point, if I go here and look up, it has an X value of -1. The X value of the rightmost point, that's an arrow. It keeps going forever and ever. There is no rightmost point, so our domain is from -1 to infinity. All X values starting at -1 and bigger for an ever and ever. There's our domain. Remember, range instead, we look from low to high, bottom to top, and we're looking for Y values. The lowest point on our graph, where it's these two, right? But they both have the same Y value. They both have a Y value of -4. So our range begins at Y equals -4. And then the highest point on the graph, again, arrow, it's going up and up and up. So again, we don't have an endpoint. We just say the range goes from -4 to infinity. Increasing, decreasing, and constant on this one. I'm going to give you a spoiler alert. There is no constant interval on this one. This one is going to be none, because unlike our last graph, we don't have a nice flat spot like we did in the middle there. This is all curvy. There's no flat spot, so there's no constant. So let's talk about what is happening. So here, I think it's pretty easy to see we're going uphill, and we keep going uphill until we get right here. And then it turns and it's going downhill, and we keep going downhill until we get right here. And then we're going uphill again. So we're increasing twice and we are decreasing once. Remember, again, we are using X values to show where those downhill areas begin and end. And uphill, downhill and uphill. So here's uphill. It begins at X equals -1. And it stays uphill, not for long. It only stays uphill until X equals 0. But we have another increasing section, right? We're increasing here as well. That's also an uphill part. And that section begins at x equals 2. And here it doesn't have an endpoint. It keeps going and going and going. So it's increasing as far as we know forever and ever after that. Decreasing is our little middle section here. Again, we want to use x values to show where that decreasing section begins and ends. Begins at x equals 0, ends at x equals 2. Sorry. Okay. Another thing we want to talk about in this section, and this is a little bit related to the symmetry that we talked about previously. Functions can be classified as either an even function or an odd function. Even function is when for each x in the domain, so every x value, f of negative x results in just plain old f of x. It's kind of like the symmetry test where we plugged in negative x and we got back our original equation, okay? So even functions are symmetric with respect to the y-axis. For an odd function, it's when we plug in f of negative x and we get out the opposite of what we started with. We do not get our original function back again. We get the entire opposite of our original function. And those are symmetric with respect to the origin. It's kind of like when we plugged in a negative x and a negative y and ended up with our original equation. So if we are asked in a section like this to figure out if a function is odd, even, or neither, all we have to do is plug in negative x and analyze our results, and we'll be able to answer our question. So here for number 5, I'm going to take that x and I'm going to replace it with negative x. So that means I have negative x to the 5th minus 3 times negative x cubed. We talked about this when we were doing symmetry. Anytime we have an odd exponent, we can take away the parentheses and the negative sign remains. That's because if we were to raise a negative number to an odd power, okay, it would still be that negative number back again. Negative 1's not a good example because these don't always match, but they did there. Like negative 2 to the 3rd is equal to negative times 2 to the 3rd, which is negative 8. So regardless, we can simplify this into negative x to the 5th minus 3 times, I'm going to simplify that a little more, right? If I take away those parentheses, I have negative 3 times negative x, which becomes positive 3x cubed. And then I am going to factor out a negative sign. Did I end up with the opposite of what I started with? If I factor out a negative sign, that becomes x to the 5th, and then minus 3x cubed. Notice that with the negative sign in front, this matches exactly what I started with, and that is the second case. That is an odd function. And that means we have symmetry with respect to the origin. And that's just by definition, once we know it's odd. Odd is always symmetry with respect to the origin. Number 6, we're going to try that same procedure. We're going to plug in a negative x. So we get negative x to the 4th minus 2 times negative x squared plus 1. So remember, even exponents clear out that negative, right? A negative times a negative gives us a positive. So negative x to the 4th is actually just equivalent to positive x to the 4th. The negative 2 remains. Negative x squared is just x squared plus 1. Compare this to what I started with. It is exactly the same. It's not the opposite of what I started with. It's exactly the same as what I started with. So this is an even function, and that means it has symmetry with respect to the y-axis. And then our next example, number 7, we're going to do that same process again. We're going to plug in a negative x, get negative x cubed minus negative x plus 1. Again, Odd exponents, we can just remove the parentheses. Odd exponent, this next one is raised to the first power, so I can remove the parentheses. When I do that, I get minus a negative x, which is plus x plus 1. No, this isn't exactly what I started with for sure, so I'm going to factor out a negative sign. Is it the opposite of what I started with? It is not. It doesn't match what I started with. It's not the opposite what I started with, so this one is neither even or odd, and that means it has no symmetry. One thing you might notice here, I don't know if you're paying careful attention, okay, notice if we have all odd exponents, like we did in number 5, it is an odd function. Okay, if we have all even exponents, like we did in number 6, it is an even function. And the thing that we need to remember that it is anytime we have a constant, like in number 6, the constant was plus 1 at the end. In number 7, the constant was plus 1. The constant counts as an even term, even exponent, okay? So if we look at number 7, we had odd, x to the third, odd, x to the first, and then the constant is even. So odd, odd, even, that's a mix, and that's why we ended up with neither. For number 5, we had an exponent of 5 and 3. Those are both odd, so that was an odd function. Number 6, we had a 4, a 2, and a constant, which counts as even, so that was our even function. Okay, I think this is the last example in this section. The zeros of functions, okay? This isn't really a new idea, maybe just some new terminology, okay? When we ask for the zeros of a function, that is asking for the x values where the function is equal to 0. The zeros are the exact same thing as the x-intercepts, okay? So if they ask us to find the zeros of the function, like for number 8, they gave us a function. What they're asking us to do is replace f of x with 0 and then solve for x. Okay, if we are asked to find the zeros of that function for number 8, we replace f of x with 0 and we solve for x. So that's what we need to do there. We need to solve that little equation for x. How about we start by multiplying both sides by x? So on the left, 0 times x is still 0. On the right, this x cancels with that x. And now we've got an easier solve. This is a nice little quadratic equation. Quadratic equations, typically we either want to factor or apply the quadratic formula. I think this one factors pretty nicely, so we're going to give that a try. X squared breaks down into x times x. I need some factors of 42 that are going to add up to negative 13. So I like minus 6 and minus 7. Negative 6 times negative 7 gives me that positive 42. And negative 6 plus negative 7 gives me that negative 13. Now that I have it factored, I set each factor equal to 0. And it turns out that this function has two zeros. X equals 6, x equals 7. So that's how we find the zeros from an equation. If they give us a graph like number 9 and they ask us to find the zeros of the function, it's super easy. You just need to know what they're asking for. They are asking you for the x-intercepts. They're asking you where is y equal to 0, okay? So the zeros of this function are x equals negative 2, x equals 0, and x equals 3. And that's it.